Okay, now I'm going to talk about series capacitors. Here we go. And we already started the conversation in the last lecture. I'm going to finish the quantitative calculation of what the value of the series capacitors will be. So what I said last time was you're going to have the same charge on the plates of each of the capacitors, which means overall that you're going to have that same charge over the single capacitor in the end. And if that doesn't make sense, look at this again. Realize this is an island, and so this charge here has to be the negative of that charge there, or they have to be of opposite sign. So if I go and calculate the capacitance of each of these, kind of like how I did for the parallel case, I'm going to say, this here? I'm going to say, okay, I know that Q1 is equal to C1 V1, and Q2 is equal to C2 V2, but I also know that Q1 is equal to Q2 for series capacitors. So therefore I can say Q is equal to C1 V1, and it's also equal to C2 V2. So that's what Q is going to be equal to for both of these. So that Q is going to be the same Q over here. It's the same Q that's across the big capacitor, the wider capacitor, I should say. So this one over here is going to be, this voltage here is going to be, as you remember, when you have voltages in series, if this is V1 and this is V2, what's going to be the voltage, the voltage across both of them here? We'll have to add them together. So if I go up this hill, I also have to go up that hill. So the total amount I'm going up is V1 plus V2. So this voltage difference across the two plates of the capacitor is V1 plus V2. That's what that is going to be, the difference in potential between those two plates. All right, so that's equal to C3 times V3 is V1 plus V2 is equal to also the same Q. So these are my equations I can use to figure out what C3 is going to be. All right, and this, of course, is V1 plus V2. So what I'm going to do now is I am going to put this like this. I'm going to say C3, which is the equivalent capacitance, C3, times V1 plus V2 is equal to Q. So C3 is equal to Q divided by V1 plus V2. And I want to go over here because I'm not sure if I'm still going to be in the view of the camera. This is the equation that I have already. And V3 is what V1 plus V2 is equal to. So therefore, I can also rewrite this as C3 equals 1 over, so if I divide the upper side by Q and the lower side by Q, note that Q is equal to C times V, so V over Q is equal to 1 over C. So this over here is 1 over C1. This over here is 1 over C2. So this is looking a lot like the parallel resistance case. The formula looks the same as the parallel resistance case. So series capacitors look like parallel resistances as far as the formulas are concerned. So I could say C3 is equal to 1 over C1 plus 1 over C2. Or if you prefer, I could say 1 over C3 equals 1 over C1 plus 1 over C2. All right, so that's where that comes from. Of course, the more resistors I put in series, the more of these I have to add up in that fashion. Okay, so this is the series capacitance formula. You already did see it used in the equation in the lab with the galvanometers right before we had to take that week off. And you're going to see it again in this week's lab, which I'll do a separate video that you can do so that you can basically do the lab virtually. All right, the last thing I want to talk about on the topic of capacitors is something called dielectrics. And what the heck are those? So what happens is, let's say in between the two plates of these capacitors, what we've been assuming actually is that there's nothing in between it. A vacuum, really. Air is a little bit like a vacuum, so it's kind of like saying there's air in between them, even though air isn't truly a vacuum. But what if there was some other material in between the plates of the capacitor, so that you have something like this? You have one plate here, this is all negatives, this is all positives. So inside, let's say I have some other material, and I'm going to draw it in a different color. I'll draw it in green, darken my green here. And this material has to be an insulator, because if it's a conductor, then you won't have a capacitor anymore, because a capacitor implies that you have charges separated here. So let's say this is an insulator. And of course, in an insulator, we talked about the fact that there's molecules in an insulator that tend to realign themselves. So the molecules in here are going to do something like this. The plus side's going to go over here, the minus side's going to go over there. I could draw all these molecules like this, with the plus side on the left, the minus side on the right. And I could go down and keep drawing that like that. Of course, there's far more than I can draw, but that gives you an idea of what's going on. This material, this green material in here that does that is called a dielectric. And conceptually what a dielectric does is, well, some insulators are going to do this more than other insulators. So they have a different quality to them. And that quality that reflects how much their molecules polarize in the presence of an electric field is summarized, so to speak, or characterized by something called the dielectric constant. And it's given by the Greek letter kappa. So the bigger the dielectric constant, then the more you're going to have this tendency to have this polarization in here. Now, what does that polarization mean? What does it cause? What's the result of it? Well, as a result of this polarization, what you're going to get is you're going to get a greater number of negative charges that can accumulate here, because you're going to have these little dipoles in here that are going to be looking positive to them. The positive side's closer than the negative side. So what that actually, the green allows you to do is to get more charges, more negative charges on this side than you would have otherwise been able to get, and more positive charges on that side than you would have otherwise been able to get. That's what the dielectric will result in. So what that actually means is you can get a bigger capacitor because you can store more charge, all else being the same. You can be able to store more charge when you have this dielectric that's inside, in between the plates of the capacitor. And so the formula gets adjusted slightly for calculating the capacitance when you have a dielectric in between, where you have the dielectric constant kappa. The new capacitance that you're going to get from a parallel plate capacitor is still epsilon 0 times A over D. You still have those factors that haven't changed, but multiplying them is the dielectric constant. The bigger the dielectric constant, the bigger the capacitance that you can get from a given arrangement. So dielectric constants can vary and come in all sorts of sizes, but they're going to be greater than 1. A vacuum is a dielectric constant of 1. Air is a dielectric constant just a tiny bit above 1. But other materials like paper, cardboard, saran wrap, other types of plastics can have much larger dielectric coefficients. So we'll actually be using those in the lab for you to increase the capacitance of a parallel plate capacitor. The other nice thing about dielectrics is they keep the plates from touching. Just having air in between there, it's hard to get them very close to each other because you need like a thin sheet of air and there's nothing that's going to keep them from touching. But if you put a piece of paper in there, you have at least something that's keeping one plate from touching the other and allowing the charges to stay separated. Okay? We'll be talking more about dielectric constants in a subsequent lecture, but this is enough for you to be able to do the lab, and there'll be a separate video on the lab where I'll do the lab, but at least you'll have an understanding of what all these concepts mean that I'm talking about. Okay, take care.